Alright, let's get started with Unit 5 of the ICP Semester 2 Final Study Guide. And let's get started. How are ionic bonds formed? Well, ionic bonds are defined by a metal plus nonmetal. And ionic bonds are formed when one valence electron of a substance or an element or atom is going to be snatched away by the other one, right? And typically these are accomplished in the form of a combination of the metal plus nonmetal. So to answer the question, how are ionic bonds formed? When an atom snatches away another atom's valence electron or electrons, plural. And so based on that question, we kind of answered this already, but what elements are most likely to form ionic compounds? Well, they're going to be metals and nonmetals. So some characteristics of ionic compounds, right? So trying to come up with a couple, right? The melting point is going to be very high, relatively high compared to other types of bonds. So let's write a couple down. High melting point. It's going to have good electricity conductivity, good electricity conductor. It will be hard, like texture-wise hard, and often brittle. Not always, but often brittle. And it will require a lot of energy to break apart, but I don't think you need to know that. So just remember these general 3 points, I guess. These are the most important ones that'll help you identify whether or not something's an ionic or covalent, along with the fact that they're either non-metal, or metal, or metal, non-metal. So ionic bonds and compounds will always be made up of one metal and one non-metal. All right. Let's move on to covalent bonds. How are covalent bonds formed, right? Covalent bonds are formed when two atoms share electrons. And they're typically, hold on, let me circle this one. They're typically nonmetals and nonmetals. Non-metal. All right, there we go. So if ionics with a metal and a nonmetal, covalent bonds are nonmetals and nonmetals. So then, what are the characteristics of covalent compounds? They're the exact opposite, typically, of ionic. So it has low melting point. It is not a good conductor of electricity, and all that jazz. All right. Question 4, what does the Roman numeral represent in the naming of an ionic compound, right? Every so often you're given something that looks like this, like iron, and then you're given, 3 there, and then you're oxide, right? What is this Roman numeral? Well, it tells you, to answer the question, it tells us charge of metal, of the transition metal. And Roman numerals are only going to be seen on transition metals and a couple of other exclusions, or because transition metals do not have a bound charge. It can be 2+, 3+, 1+, and all that jazz. So it will tell you the charge of the transition metal plus a few extras. Okay, fill in the prefixes below, and these are the rules for covalent naming. So the non-metal naming, right? So I mean, you get a note card, right? But it's best to just memorize these, right? But if you can't, there's always a note card. So starting with mono for 1, we have 2 for di, 3 tri, and then we have 4 is a little hard to remember, but it's tetra. 5 is penta, pentagon. 6 is hexa, hexagon. 7 is hepta, heptagon. It's easy to remember with shapes for these. Octa for 8, nona for 9, and deca for 10. So the only weird one you've probably never seen is going to be 4 for tetra. And so as long as you remember this one, you should be all set. Alright, I hope this is bringing back your memory. Let's get to naming some of these. Wow, so fun. So we first identify if it's ionic or covalent, and then we can name. Because remember, there's different rules for ionic naming and covalent naming. For ionics and covalents, there's very drastic differences, and we'll go over them, but let's first identify whether or not these are ionic or covalent. Ionics are defined by a metal plus a non-metal, and covalent is defined by non-metal plus non-metal. So let's see if we have any metals in our formula given. Well, Al, aluminum, is certainly a metal, so I would say this is very ionic to me. And to name this, all we have to do is look at this and say, is this non-metal a diatomic, or not diatomic, polyatomic ion, right? Polyatomic ions are on the back of your periodic table, and if it's not on the back of your periodic table, then it's not a polyatomic ion. So if it's not a polyatomic ion, which in this case it is not, we just say aluminum, right? The first atom, the metal, always keeps its name, and then we say aluminum, and since it's chlorine, right, we change the "ine" to "ide", and we call it aluminum chloride. Okay, let's take a look at this next one. This next one is CCl4. So C is one atom and Cl is another atom. And they're both nonmetals, so they're going to be covalent. So given covalent naming, all we have to do is figure out the number of each atom and just put them at the end of, or the beginning of it. But remember that the first atom in the compound, the C, the carbon, even if there's one carbon in it, it does not get the mono in front. So you would not call this monocarbon. That's a big no. And you would just call it regular carbon. You do not put mono in front of a non-metal first element. So you just call this carbon. And then how many of the chlorines do you have? We have 4. So we have tetrachloride. Remember, we changed this to the "ide", and then we put the prefix that we wrote on top of your paper, just on question 5, in front of the respective atom. Next one, we have sulfur tetrafluoride, which is SF4, and those are going to be both nonmetals, therefore it's covalent, right? And so in order to put the name or formula, right, I just kind of spoiled it, sorry, but we look at the name, right? Then the rule was that we don't put anything in front of this first atom if it's just one of it. Like, remember here, we only had one carbon, so we didn't put anything in front of it. And so that would tell us we have 1 sulfur. And of course the suffix tetra means 4, which means we have 4 fluorides, which is fluorines. And therefore the compound name is SF4. Next up we have SiO3. Si is silicon and O is oxygen. Therefore both two nonmetals are going to be covalent. Alright, and in order to name this, we're going to have just silicon, because there's nothing in front of this if there's only one. And we're going to have trioxide. Remember, oxygen is a little special. You put oxide instead of oxygen. So oxide, and you add that tri because there's 3 in the compound. Next up, we have iron 2 sulfate. Remember that special occasion we talked about with the Roman numerals? They only occur with a transition metal and, of course, a couple exclusions. But we know iron is a metal. Iron is a metal, and sulfate is on the back of your periodic table as a polyatomic ion. And if you look down and find it, sulfate is going to be SO42-. So we know this is ionic because iron is a metal. And this number in the parentheses, the Roman numeral, tells us the charge of the iron and tells us that it's 2+. Metals are always 2+, or positives. So we know iron has a 2+ charge and sulfate has a 2- charge. These charges cancel out. And then you're left with just FeSO4 as the formula. All right. Next up, we have MgNO2. Magnesium, Mg, is a metal. Ionic compound it is. And to write this, we would use the Roman numeral, the ionic rules. In this case, we do not use the Roman numerals because magnesium is a metal with a defined charge. It is not a transition metal. Right, if you look on your periodic table, element 12 is going to be magnesium. Magnesium holds a 2+ charge. All right, and this right here, the NO2, this is technically going to be classified as one atom in this case because it's a polyatomic ion. The name for this is nitrite. Let me draw an arrow here. Nitrite, right? And then all you're going to do is use the normal naming rules for metals. You're going to put magnesium and then nitrite. That's a polyatomic ion once again, and you're all set. Next up, we have silicon dioxide. Silicon is once again a nonmetal. Oxide, standing for oxygen, is also a nonmetal, which makes it a covalent compound. Silicon's symbol on the periodic table is Si, found on number 14 on your periodic table. We only have one of this because there's no suffix in front of, or prefix in front of it. And we know that oxide means oxygen and di means 2. So we have 2 oxygens. That's horrible O's. All right, there we go. SiO2. Last but not least, we have magnesium chloride. Magnesium is once again a metal, as we saw up above here. And chloride is a nonmetal. So this is going to be ionic. And we first determined the charge of magnesium as 2+, because it has 2, it's in group 2. And chloride as 1-, because it's a halogen. It's number 17 on your periodic table. So with this information, we know that to convert this into a neutral charge, for every 1 magnesium with a 2+ charge, we need 2 chlorines with a 1- charge each. So therefore, our formula is going to be MgCl2. For every 1 2+ magnesium, we need 2 1- chlorines. And that brings us to the end of Unit 5, and we'll see you next for Unit 6, Chemical Reactions. Thank you.